Welcome to the session Particular Integral of Solutions of Differential Equations and Cauchy's Equations. The general solution of a non-homogeneous linear differential equation a0 d raised to n plus a1 d raised to n minus 1 plus etc. plus a n minus 1 d plus a n of y is equal to x, let it be equation number 1, where a0 not equal to 0, x not equal to 0 and a0, a1, etc. a n are constants is y is equal to yc plus yp. Here yc and yp are respectively known as the complementary function cf of the solution and particular integral pi of the solution. The complementary function is the general solution corresponding to the homogeneous differential equation a0 d raised to n plus a1 d raised to n minus 1 plus etc. plus a n minus 1 d plus a n of y is equal to 0, which contains n arbitrary constants. Particular integral. The particular integral of the solution is the function which is a particular solution of equation number 1 containing no arbitrary constant. The particular integral depends on the right hand side function and is defined as pi is equal to 1 by f of d of x, where 1 by f of d is the inverse operator of f of d. That is, f of d of 1 by f of d of x is equal to x. Theorem. If x is a function of x, then 1 by d minus m of x is equal to e raised to mx into integral x e raised to minus mx dx. Proof. Let 1 by d minus m of x is equal to y. Operating both sides by d minus m, we have d minus m of 1 by d minus m of x is equal to d minus m of y, which implies x is equal to dy minus my, which implies dy by dx minus my is equal to x, which is a linear differential equation. Its solution is y into e raised to minus mx is equal to integral of x into e raised to minus mx dx, which implies y is equal to e raised to mx into integral x e raised to minus mx dx. Hence, 1 by d minus m of x is equal to e raised to mx into integral x e raised to minus mx dx. Now, we shall discuss the method of finding particular integral corresponding to different functions. When the right hand side function is x is equal to e raised to ax, where a is a constant. In this case, the particular integral is 1 by f of d of e raised to ax is equal to 1 by f of a into e raised to ax, provided f of a not equal to 0. If f of a equal to 0, then the particular integral pi is equal to x into 1 by f dash at a into e raised to ax, provided f dash a not equal to 0. If f dash a equal to 0, then the particular integral pi is equal to x square into 1 by f double dash at a into e raised to ax, provided f double dash at a not equal to 0. If f double dash at a is equal to 0, then the particular integral pi is equal to x cube into 1 by f triple dash at a into e raised to ax, provided f triple dash at a is not equal to 0, and so on. For example, for the equation d cube plus 2 d square plus d of y is equal to e raised to 2x, the particular integral is pi is equal to 1 divided by d cube plus 2 d square plus d into e raised to 2x, that is equal to 1 divided by 2 cube plus 2 into 2 square plus 2 into e raised to 2x, which is equal to 1 by 18 into e raised to 2x. For the equation d raised to 4 minus 2 d cube plus d square of y is equal to e raised to x, the particular integral pi is equal to 1 by f of a into e raised to x, which is equal to 1 divided by 1 raised to 4 minus 2 into 1 cube plus 1 square into e raised to x, which is equal to 1 by 0 into e raised to x, which is failure. Therefore, pi is equal to x into 1 divided by f dash at a into e raised to x, which is equal to x into 1 divided by 4 into 1 cube minus 2 into 3 into 1 square plus 2 into 1 into e raised to x, which is equal to x into 1 by 0 into e raised to x. which is also failure. Therefore, the particular integral pi is equal to x square into 1 divided by f double dash at a e raised to x, which is equal to x square into 1 divided by 12 into 1 square minus 12 into 1 plus 2 e raised to x is equal to x square into 1 by 2 e raised to x. When the right hand side function is x is equal to sin ax plus b or cos ax plus b. In this case, we write the operator polynomial f of d as a function of d square. The particular integral is pi is equal to 1 by f of d square into sin ax plus b, which is equal to 1 divided by f of minus a square sin ax plus b, provided f of minus a square not equal to 0. If f of minus a square is equal to 0, then the particular integral pi is equal to 1 divided by f of d square sin ax plus b, which is equal to x into 1 divided by f dash at minus a square sin ax plus b, provided f dash at minus a square not equal to 0. If f dash at minus a square is equal to 0, then the particular integral pi is equal to 1 by f of d square sin ax plus b is equal to x square into 1 divided by f double dash at minus a square sin ax plus b, provided f double dash minus a square not equal to 0, and so on. A similar result is obtained by replacing sin ax plus b with cos ax plus b. For example, for the equation d square minus 4d plus 3 of y is equal to sin 3x, the particular integral pi is equal to 1 divided by d square minus 4d plus 3 sin 3x, which is equal to 1 divided by minus 9 minus 4d plus 3 sin 3x, which is equal to minus 1 divided by 6 plus 4d sin 3x is equal to minus 1 divided by 2 into 2d plus 3 into sin 3x, which is equal to minus 1 by 2 into 2d minus 3 divided by 4d square minus 9 sin 3x is equal to 1 divided by 9d into 2d minus 3 of sin 3x, that is equal to 1 by 9d into 6 cos 3x minus 3 sin 3x, that is equal to 1 by 30 into 2 cos 3x minus sin 3x. When the right hand side function is x is equal to x raised to m, where m is a positive integer. In this case, the particular integral is pi is equal to 1 by f of d of x raised to m, which is equal to f of d all raised to minus 1 of x raised to m. Now expand f of d all raised to minus 1 using binomial theorem up to the term d raised to m and operate on x raised to m term by term. For all higher derivatives, that is d raised to m plus 1, d raised to m plus 2, etc., x raised to m will be 0. Example, for the equation d plus 1 of y is equal to x cube, particular integral is equal to 1 by d plus 1 of x cube, which is equal to 1 plus d all raised to minus 1 of x cube, which is equal to 1 minus d plus d square minus d cube plus etc. of x cube, that is equal to x cube minus 3x square plus 6x minus 6. And for the equation d into d square plus 1 of y is equal to x square plus 2, the particular integral pi is equal to 1 divided by d into d square plus 1 of x square plus 2, which is equal to 1 by d into 1 plus d square all raised to minus 1 into x square plus 2, that is equal to 1 by d of 1 minus d square plus etc. of x square plus 2, which is equal to 1 by d of x square plus 2 minus 2, that is equal to 1 by d of x square is equal to x cube divided by 3. When the RHS function is x is equal to e raised to ax into v being a function of x. In this case, the particular integral is pi is equal to 1 by f of d of e raised to ax into v, that is equal to e raised to ax into 1 by f of d plus a of v. Example, for the equation d square minus 2d plus 1 of y is equal to x e raised to x, the particular integral pi is equal to 1 by d square minus 2d plus 1 of x e raised to x, which is equal to e raised to x into 1 divided by d plus 1 whole square minus 2 into d plus 1 plus 1 of x, that is equal to e raised to x into 1 divided by d square of x, which is equal to e raised to x into 1 divided by d of x squared by 2, which is equal to e raised to x into x cube divided by 6. When the right hand side function capital X is any other function of x. In this case, resolve f of d into linear factors. Let f of d is equal to d minus m1 into d minus m2 into etc. into d minus mn. Then the particular integral pi is equal to 1 by f of d of x, which is equal to 1 by d minus m1 into d minus m2 into etc. into d minus mn of x, that is equal to a1 divided by d minus m1 plus a2 divided by d minus m2 plus etc. plus an divided by d minus mn of x by partial fraction, that is equal to a1 into 1 by d minus m1 of x plus a2 into 1 by d minus m2 of x plus etc. plus an into 1 by d minus mn of x, that is equal to a1 into e raised to m on x into integral x e raised to minus m on x dx plus a2 into e raised to m2 x into integral x e raised to minus m2 x dx plus etc. plus an into e raised to mn x into integral x e raised to minus mn x dx, since 1 by d minus m of x is equal to e raised to mx into integral x e raised to minus mx dx. Example: for the equation d square plus a square of y is equal to sec ax, the particular integral pi is equal to 1 by d square plus a square of sec ax, which is equal to 1 by d minus ia into d plus ia of sec ax, that is equal to 1 by 2 ia divided by d minus ia minus 1 by 2 ia divided by d plus ia of sec ax, which is equal to 1 by 2 ia into e raised to iax integral e raised to minus iax sec ax dx minus 1 divided by 2 ia into e raised to minus iax integral e raised to iax sec ax dx, which is equal to 1 by 2 ia into e raised to iax integral 1 minus I tan ax dx minus 1 by 2 ia into e raised to minus iax integral 1 plus I tan ax dx, which is equal to 1 by 2 ia into e raised to iax into x minus I by a log sec ax minus 1 by 2 ia into e raised to minus iax into x plus I by a log sec ax is equal to x by a into e raised to iax minus e raised to minus iax divided by 2i minus 1 by a square into log sec ax into e raised to iax plus e raised to minus iax divided by 2, which is equal to x by a into sin ax minus 1 by a square into cos ax log sec ax. Note: this case can be considered as a general case. If the right hand side function contains a combination of the above discussed functions, then particular integral of the solution can be obtained by adding the particular integrals of each term. Cauchy's equation: an equation of the form a n x raised to n into d raised to n y divided by dx raised to n plus a n minus 1 into x raised to n minus 1 into d raised to n minus 1 y divided by dx raised to n minus 1 plus etc. plus a1 x into dy by dx plus a naught y is equal to q of x, where a naught comma a1 comma etc. comma a n minus 1 comma a n are constants is called a Cauchy-Euler equation of order n. To know the solution of such an equation, we make some suitable substitution so that the equation may reduce to an equation for which the methods of solutions are known. Such a substitution is x is equal to e raised to t. This substitution reduces the equation into a linear equation with constant coefficients. Put x equal to e raised to t, then log x is equal to t. dy by dx is equal to dy by dt into dt by dx is equal to dy by dt into 1 by x, which implies x into dy by dx is equal to dy by dt, which is equal to dy. D square y by dx square is equal to 1 by x into d by dx of dy by dt plus dy by dt into d by dx of 1 by x, which is equal to 1 by x square into d square y by dt square minus dy by dt. Therefore, x square into d square y by dx square is equal to d square y by dt square minus dy by dt, which implies x square into d square y by dx square is equal to d square minus d of y, which is equal to d into d minus 1 of y, etc. In general, x raised to n d raised to ny by dx raised to n is equal to d into d minus 1 into d minus 2 into etc. into d minus n minus 1 of y. Substituting these values in the given equation, we obtain linear equations with constant coefficients and can be solved by already known methods. Example: solve x square d square y by dx square minus 4x dy by dx plus 4y is equal to 1 plus x whole square. Solution: putting x is equal to e raised to t and so log x is equal to t. Therefore, the given equation reduces to d square minus 4d plus 4 of y is equal to 1 plus 2 e raised to t plus e raised to 2t. To find the complementary function, the auxiliary equation is m square minus 4m plus 4 is equal to 0, which implies m minus 2 whole square is equal to 0, which implies m is equal to 2 comma 2. Therefore, the complementary function Cf is equal to C1 plus C2t into e raised to 2t is equal to C1 plus C2 log x into x square. To find the particular integral, Pi is equal to 1 divided by d square minus 4d plus 4 of 1 plus 2 e raised to t plus e raised to 2t, which is equal to Pi1 plus Pi2 plus Pi3. Pi1 is equal to 1 divided by d square minus 4d plus 4 is equal to 1 divided by d minus 2 whole square of 1, which is equal to 1 divided by 4 into 1 minus d by 2 whole square of 1, which is equal to 1 by 4 into 1 minus d by 2 whole raised to minus 2 of 1, which is equal to 1 by 4 into 1 plus d plus etc. of 1 is equal to 1 by 4. Pi2 is equal to 1 divided by d minus 2 whole square of 2 e raised to t, which is equal to 2 into 1 divided by d minus 2 whole square of e raised to t, that is equal to 2 e raised to t, which is equal to 2x. Pi3 is equal to 1 divided by d minus 2 whole square of e raised to 2t, that is equal to t into 1 divided by 2 into d minus 2 of e raised to 2t, which is equal to t square into 1 by 2 e raised to 2t is equal to x square into log x whole square divided by 2. Therefore, the complete solution is y is equal to Cf plus Pi, which is equal to C1 plus C2 log x into x square plus 1 by 4 plus 2x plus x square into log x whole square divided by 2. Let me summarize the major points discussed so far. An equation of the form a naught d raised to ny divided by dx raised to n plus a1 d raised to n minus 1 y divided by dx raised to n minus 1 plus etc. plus a n minus 1 dy by dx plus a n y is equal to x, where a naught, a1 etc. a n, x are either functions of x or constants and a naught not equal to 0 is called a linear differential equation of order n. The general solution of a non-homogeneous linear differential equation is y is equal to Cf plus Pi. The complementary function Cf is the general solution of corresponding homogeneous differential equation. The particular integral of the solution is the function which is a particular solution of the given equation containing no arbitrary constant and is defined as Pi is equal to 1 by f of d of x, where 1 by f of d is the inverse operator of f of d. It depends on the right hand side function x. The general form of Cauchy's differential equation is a n x raised to n d raised to n y by dx raised to n plus a n minus 1 x raised to n minus 1 d raised to n minus 1 y divided by dx raised to n minus 1 plus etc. plus a1 x dy by dx plus a naught y is equal to q of x, where a naught, a1 etc. a n minus 1, a n are constants. Now, you can try to solve the following questions. First one, d square plus 2d plus 1 of y is equal to x cube plus cos 2x. Second one, d square y by dx square plus dy by dx is equal to x square plus 2x plus 4. Third one, d square y by dx square plus y is equal to e raised to 2x plus cos h 2x plus x cube. Fourth one, d square minus 2d of y is equal to e raised to x into sin x. Fifth one, d square plus 2 of y is equal to x square into e raised to 3x plus e raised to x into cos 2x. Sixth one, d minus 1 whole square into d plus 1 whole square of y is equal to sin square x by 2 plus e raised to x plus x. And the seventh one, x cube into d cube y divided by dx cube plus 3x square into d square y by dx square plus x into dy by dx plus 8y is equal to 65 into cos log x. You may go through the following books for your further reference. Differential Equations and Their Applications, second edition by Zafar Hassan, Prentice Hall, Publishers, New Delhi, 2006. Differential Equations by George F. Simmons, Tata McGraw-Hill's Publishers, New Delhi, 1996. Differential Equations, third edition by L. Ross, Wiley Publishers, New Delhi, 2009. Differential Equations and Their Applications by M. Braun, Springer Verlag, Berlin, 1975. Elementary Differential Equations, 6th edition by L. M. Kelly, McGraw-Hill's, New York, 1965. Hope that you have enjoyed this session. We will meet again with another topic. Thank you.